Thank you all. Thank you for coming again. Thank you for joining us, having me here. It's an honor. So we have everything ready, set, let's go. Before we actually proceed, I want you to picture this. One platform, manual processes, no real source of truth, and 400 plus clusters, manual tools. For me, sounds like we have a challenge. My name is Petrica. I'm a software engineer at Adobe. This is our story and how we made it work. So here's where we are headed. This is our roadmap. We will start with an introduction, the problem, and where we were. Then we will discuss the legacy platform, how it was built, how it worked, and how it eventually broke down. Then we will discuss the modern platform, its architecture, cluster lifecycle, and we'll have a short demo as well, so we don't speak only theoretically. And we will end with some key takeaways. So here we are at the beginning, where we were and how we knew something had to change. I hope everyone was here at least once in their career, and if not, you should try harder. You write your code, you test it on your local, it works. Okay, my Jira ticket will be completed by end of the day. Then you raise a PR, you have the CI/CD passing, you are happy, you tick that out of the box. You have all the compliance, audit, ready, and then you go to the last step, deploying it on a Kubernetes cluster. This is where things go south. It takes at least 3 days, one Jira ticket, a lot of nerves to get it done. Well, that's on us as platform engineers, and I personally cannot live with that. So to understand the platform first, you have to understand its customer and products. So let's start from here. Adobe runs 3 major clouds. We have Creative Cloud, we have Document Cloud, and Experience Cloud, with products that you might use on a daily basis, like Photoshop, Premiere, DocSign. But the key thing is that each one of them has its own dedicated platform. Let it be content platform, data platform, AI/ML, and others. And underneath all these, we have our internal platform engineering layer, our main topic today, the Adobe platform. And this platform, the foundation, spans AWS, Azure, and our own data center. Now that we know the platform, I think the most important thing to talk about it's numbers. This is how we are today. We have 280 clusters on AWS, 155 clusters on Azure, and a smaller footprint on our own data centers. What's even more important about the numbers is how our fleet grew over time. We started with the legacy platform back in the day, just a few clusters. It was designed for that kind of clusters, and over time it grew dramatically. Not exponentially, but the multiplication factor became too big for the legacy platform to handle. And I want you to keep in mind this slide, because I'm gonna talk about it later on. Now that we mentioned legacy platform, let's deep dive into it. Discuss how it was built, how it worked, and how it eventually let us down. So the legacy platform was mainly a Python monolith that interacted directly with the cloud provider API. Its core issue, it was that there was no clear separation between infrastructure and configuration. And as you saw 2 slides before, it became really hard to scale with a growing number of cluster requests. So we ended up having long delivery queues. This is the structure of the legacy platform. We have in the same repository, we have the infrastructure, where we have different cluster types on different cloud providers, and the binary, the entry point, the configuration, where if we change anything, then it changes the whole show for the infrastructure side. Now we will focus on a real-world example that, as we talked in the beginning, every platform team has to do it regularly. Cluster upgrade. So our goal is to upgrade our cluster from 131 to 132. So I make the changes, I push them to Git, I have the SHA over there. In the legacy platform, the next step is to run that through an Azure DevOps pipeline. I know what you're thinking now. So we have two artifact repositories, one for configuration, one for infrastructure, and we already see the core issue. They are bundled together and deployed as one. And see for infrastructure, you see my SHA from the previous commit with a change. On top of this, it gets even worse. We have to manually fill some variables, like who runs the pipeline, do we want integration tests, and the most important one, the command, which is a chain of make targets, hoping that I don't do a typo, and whoever runs the pipeline know what they are doing. So it gets really tricky from here. Now we will focus on AWS as cloud provider, but I want you to keep in mind that these rules apply to the other cloud providers as well. So after I trigger the pipeline, behind the scenes, the pipeline will interact with 5 CloudFormation stacks in AWS, each of one designated for specific layers, like network, monitoring, ingress, and others, and with the cluster itself. But the issue is that the pipeline has to orchestrate all these dependencies in the right order and at the right time. So basically, we rely only on a pipeline. Now we have to ask ourselves the question, why a simple upgrade was never simple, now that we know how we do it? Well, our goal, as we started, was to upgrade the cluster from 131 to 132. But because infrastructure and configuration were bundled and deployed together, we had some unrelated changes as well. We had the Windows image update, the Lambda change, the LCD server, which were not correlated with our change. So let's say, what happens if something breaks along the way? Will it come from my update? Will it come from the LCD server? I have to troubleshoot and see where the hiccup is. Well, we saw the main issue. One change would mean all earlier commits have to be deployed. Now that we experience all the legacy platform, let's draw some lines with its limitations. We started by saying that we have a monolith design in Python. That means infrastructure and configuration are bundled together. So every change, we had to redeploy everything. Then we saw that we have sequential pipelines to Azure DevOps. No parallelism, or not that much, slow throughput. We have limited observability because we bundle all the changes. I don't know if there is an error or if something breaks. I don't know what the origin of the error is. So I have to slow troubleshoot and recovery that. As we saw in the previous slides, it became hard to scale with the growing number of cluster requests. And we ended up having long delivery queues. Product teams would have to wait weeks for us to provision them a cluster. And it was hard to cancel a running pipeline mid-upgrade. If I found out there was a typo or there is an incident, so I need to stop the upgrade, I wouldn't only have to tick a cancel box. I also have to run another job that kills my background process. So it's slow response in case of an incident, and I might leave the cluster in a partial state. I think this slide speaks by itself. I think the bravest thing a platform team can do is to acknowledge that what they build no longer serves the customer or even themselves. So that's where innovation comes in place. And speaking about innovation, here we are, the modern platform. This is where it gets spicy at all, yeah. So talking about the modern platform, let's draw its goals. We build the goals of the modern platform by taking the hiccups of the legacy platform. And with that, we wanted to decouple infrastructure from configuration so changes are scoped and safe. We wanted to deploy changes in a targeted way without the blast radius. And to have all these two together, we wanted to adopt a GitOps-driven model so Git will become the real source of truth for clusters, for configurations, and for cloud resources. Speaking about the GitOps model, this is how we use it. We have infra and configuration separately, and then there is GitOps operator, Argo CD in this case, that continuously pulls data from Git and reconciles them against the actual clusters. No manual pipelines to babysit anymore. So the cluster is always converging towards what Git says. Now, how does our platform work where it stands? So our platform stands on three main pillars. We have the desired state, we have the management cluster, and we have the multi-cloud Kubernetes fleet. Starting from left to right, in desired state, we keep cluster and add-on configuration, security and audit compliance policies. Everything in Git, everything declarative. Then in the middle, we have the management cluster, which actually has two roles. We have the observe role, which is done by GitOps operator, Argo CD, that pulls data from Git and changes the infrastructure objects on the management cluster. And on the other side, we have provision and reconcile role, which is done through ACK and ASO cloud provider specific controllers and copy for the cluster that take those infrastructure objects and applies them in the actual cloud. And to the right, we have EKS and AKS fleet continuously converging towards what Git says it should be. Now, this is the magic behind these controllers, ACK, ASO, and copy. You define your own Kubernetes object that defines a VPC in this case. I fill the name, I fill the tag, I set the region, then the CIDR block, and ACK translates that into an actual VPC in AWS, as you can see down there. No Terraform, no CloudFormation, no other tooling. The same API that you use to manage your cluster now manages your cloud infrastructure. We saw how to create a new resource, but what happens with the existing resources? Do I have to recreate them? Well, these controllers actually let you import your resources through these two annotations, which is adoption policy, which can be adopt and adopt or create, and the adoption field, which is the lookup key to tell the controller where to look for the resource in the cloud provider. Then for the adoption policy, as I said, it can be adopt if you only want to adopt that resource under the manage of the controller, and adopt or create, so if it cannot find the resource, it will create it for you according to your spec. And spec is also populated by the controller depending on the policy. If it's only adopt, then it fetches the configuration from the provider, and if it's create, you will always change the object according to your spec. Now, how does a cluster look in the modern platform? We have three layers. We have the ACK layer, where we build the infrastructure required by the cluster. We have network, security, storage, and IAM. On top of this, we come with the cluster itself through copy. So we build the cluster by binding the cluster with the required infrastructure. Now we have an empty cluster, but it's not ready yet. On top of that, we come with our admin apps, Envoy, Cilium, Core DNS, and that makes an Adobe production-ready, safe, and compliant cluster where production teams can now deploy their applications. This is an end-to-end, this is the management cluster. I mentioned it a few times, but I didn't really tell you how we use it or what it is. So you saw that the first layer for the cluster is the ACK layer. But where does those objects live, right? Because they cannot live on the cluster since we come with that at the next level. This is where management cluster comes into play. The management cluster is a cluster where we store the infrastructure objects and the controllers for them to provision the actual infrastructure required by the cluster. And the way we do that is to isolate them in a dedicated namespace for each cluster where we have the objects that are reconciled by the controllers. And they are linked to the actual clusters where the admin apps are running. No more CloudFormation stacks, everything is clear, designed as it should be in 2026. Now this is an end-to-end overview of how to get the change deployed onto your cluster. And in this overview, we have built a shared responsibility model. We have the operator responsibility, which does the changes and pushes them into Git. And we have the ACK and copy controls responsibility, which takes those changes and applies them on the actual clusters. And obviously we needed a manager of this relationship, and this is where IO came into place. So it takes the changes from Git and it applies them on infrastructure objects where they are taken by the controllers and applied in the cloud. Now that we've mostly spoken theoretically, let's get into practice. What I'm going to show you now, it's a cluster upgrade in the modern platform from version 131 to 132. So sit back, relax, and enjoy the show. Okay, so we saw how easy it is to upgrade your cluster in the new platform. For the control plane, it only required one line of change. We went there, we changed the Kubernetes version from 131 to 132. Then once that was in Git, Argo CD took that change and applied it on my infrastructure object. And then it was taken by copy and applied it on the actual cluster. On the other side, for workers, we had two lines of change. We had to bump the architecture, the AMI for both architectures, for AMD and ARM. Then Carpenter took that change and rolled it out for us. We got 132 nodes, and we started draining the 131 nodes. So we had 2 files, 3 lines of code, 2 commits. Compare that with the previous platform, where we had to run the pipeline manually, deploy it on 5 CloudFormation stacks, babysit, and hope that nothing will break. That was a gamble, and now this is a safe, compliant upgrade without any headache. I will take this at any time in my life, actually. So here we are at the end. Let's wrap it up. So what does this mean for our customers deploying on our platform? Well, it means less waiting days for a new cluster to start deploying. Everything is faster, secure, reliable. Customize your Adobe cluster is fast and efficient. Now, there is only one PR in a repository that gets reviewed by the platform team, and anyone can do it. No more Jira tickets to the platform team. And everything is predictable, transparent, thanks to the GitOps-driven model. Everything is declarative, everything is in Git. Well, this was our story with its ups and downs, late nights, a lot of sweat, a lot of nerves, and moments where we thought it might not work, but it goddamn did. And here we are. My team is always in the room. I want to thank you all for coming and putting all this hard work. Was one hell of a job. So I hope all of you can take anything out of this back into your own platform. Thank you, and I'm ready to have your questions.
Awesome, thank you so much. I got a first question. I hope that you cannot in your production environment just bypass all of your rules when you do a commit to Git.
Yeah, that was a dev cluster.
Yeah. Any questions in the room? Yeah, here we go.
Okay, if I understood you well, you have custom resource definition that your operators use to deploy the target clusters to the production. And how this custom resource definition, did it become complicated? Did it become like 20,000 lines of code, or how do you serve all small customization to the clusters by custom resource definition?
Yeah, so by custom definition, we have all the Helm charts defined for every layer, let's say network or IAM roles. Let's say they want an extra security group for any port or something dedicated for them. Like we have all the charts defined for the platform itself that should be on all clusters. And when they want to custom, let's say security group, ingress, or even knuckles or subnets, they just raise a PR. We have a place where we store the configuration for all clusters, where all these operators for network read from, and they put there the extra port or the extra security role. Basically they have to know basically the charts. It's easy because it's human readable, and we make them clear for the customer to understand. Like it will be like security extra worker rules, and then put the port or the rule, as easy as that. So that's what I meant by customization for tenants. If they require something, they can either ask us, or if they've done it before, they know the process. It's just 2 lines of code, basically, or something.
So how do you orchestrate different operators? If you need to create cluster to apply network configuration, I guess. So how do you orchestrate those operators between them?
That's where management cluster comes into place. Because in each namespace so the management cluster, as I pointed out, is a cluster where we store for each cluster in a separate namespace the infrastructure objects. So basically all the changes go there, and then they are binding to the actual cluster. And that management cluster is not even known by the customer, let's say. It's only for the platform team. I can take this offline if you want, it's fine.
Here we go.
Hello, great presentation. I do have a question regarding how you handle upgrades. You showed that it's quite easy to upgrade, but what do you do about upgrade impact level changes that you would have to take into account? For example, a couple of years ago, if you wanted to upgrade Kubernetes from 123 to 124 maybe, I'm not exactly sure, you had to install the EBS CSI plugin in your EKS cluster. Otherwise, your entire workloads would become unavailable because they would no longer have access to the CSI storage from Amazon. And secondly, you upgrade the cluster. Do you also upgrade operators like the CNI, CSI, and so on and so forth? Or those remain in the past?
Yeah, thank you. So for the first question, that was copy controller comes into place. So that's an open source controller. And let's say if there's a case like that, we might have to upgrade the version of the copy controller. So when we do the upgrade, it will support any kind of change that was released in the coming years or something that is supported or not supported in the previous versions. And to the second one, it doesn't come as part of the upgrade, but we do that regularly for CNIs. Yeah, so we do that regularly, but it doesn't come as part of the upgrade itself. Have I answered your question?
Maybe a longer discussion in the break.
Yeah, sure.
We have 3 more minutes. I have a question while I find for the next speaker. You mentioned AWS and Azure.
Yes.
Have you introduced an abstraction layer on top of both cloud providers or not?
I think that's a separate presentation.
Okay.
Yeah. I might do it next year.
Any other question? Here we go.
Thank you. So how would this map on multiple AWS accounts? I mean, I assume you have multiple AWS accounts, an organization, and before you create a cluster for a client, you probably would need an account, and in that account, you'd create further resources. But
yeah, so
I'm curious.
Yeah, so the controller themselves that run on the management clusters, we actually create a role in the target account, and the controller from the management cluster assume that role, so it then creates the infrastructure through pass role. So we have IAM pass role that goes from the source account, the management cluster, to create infrastructure in the targeted account, different org, different account. So we require a role that can create infrastructure that is assumed from the management cluster.
So the account is already there when starting?
Yes, when we create new clusters, the account is there for that organization, and the way we create resources, yeah, it's you're assuming an IAM role that can create infrastructure.
Awesome. So I would say you heard from the other room that they can applaud really loud. At least I heard this. I think we can applaud louder.
Woo!
And as you said, it seems there's a lot of discussions that will maybe happen in the hallway. So
yeah, I will take them offline. Yeah, thank you for coming again, and hope you like the presentation.
Awesome. Now, a reminder, the next 2 sessions, there's a 15-minute break. The next session in here is going to be at 2:45, scaling blockchain infrastructure to billions of requests. And the parallel session over there is going to be MLOps for GenAI, enabling auto-scaling for GPU-intensive workloads. Take the break for filling up your sponsor passports, take a selfie at the selfie booth, and be back in 15 minutes.